Now, once I get this going, I can't see but like a couple of people. So if you see anyone else come into the class, please let me know so I can get them on the roll. Has anyone come in the last few minutes and you have not heard me acknowledge your name? Have you seen anybody pop up? Okay. Just to let you know, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 people showing, plus me is 12. Do you see any more than that? Say again?
That's right.
That's right. Okay. So how have you been? I gave you my good news. At least it's nice not to give you bad news one time. How have y'all been? Any problems, issues, or other things? Everything's okay?
I got one question.
Okay, what's that?
When you evaluate, when you're doing synthetic division, and like if you got f of 6, you change that to -6, right?
Okay. Now, all right. I'm not sure I understood the question. You said something about having something like alpha 6, and you said,
When you're doing the synthetic division,
oh, synthetic division. Okay, got you. Okay, synthetic division. I missed that part. All right. Now, it sounds a little confusing, but hopefully it sort of makes sense. When you're dividing x, you want it plus or minus? I don't care. You pick. Plus, okay. If you're dividing x plus 6 into another polynomial, then in synthetic division, what you put outside the box is a -6. If that was x minus 6 going into the polynomial, then you put a plus 6 outside the box and go from there. Now, if you're evaluating a function at x equals 6, okay, now what I'm going to do, and I'll try to do it here. If you think about this, let me see, yeah, let me get my pen set up here. Okay. If you think about this, x plus 6, can you see where I'm writing at the top of the screen there? X plus 6, you change that to a -6. But if you're evaluating it, say at x of 6, that means f of 6, that means x equals 6. Well, if you were to move that 6 to the other side, that would have been an x minus 6. So that would not be the same. F of 6, you put the 6 on the outside and the polynomial there. So if you're doing a factor, x plus 6, you change the sign. If you're evaluating at x equals 6, you leave the sign just like it is. Did that answer what you're asking?
Yes, sir, I got it.
Good. All right. Good question. Excellent question. I see so many students get that confused. I'm so glad you asked. Any others? Great questions. Okay. Did you say when or how? How? Okay. You got about 4 different, well, 5 maybe different possibilities. So let me give you what they are. First, when you finish a test, you can either scan the test or take a picture of it if you don't have a scanner. Like we don't have our scanner set up here at the house now. We have so many things set up, we just don't, the office isn't big enough for the scanner. So you can either scan it or take a picture of it. Now, if you take a picture of it, try to get really good light and not get it in the shadow and that kind of stuff. So try to take a real clear picture. I can usually handle most pictures, but some of them get really, really dark. So try to do the best you can with the picture. Now, once you have the either scanned or the picture, now when I say take a picture, I mean with your cell phone, with your smartphone. Okay? Now, once you have that as a file, either as a PDF file from scanning or whatever it is from taking a picture, then you can attach that either to an email and send it to me by email, or you can attach it to a message in Blackboard and send it to me via the message. Okay. Does that And then the other option, like I got one from one of the students in this class yesterday. She's not here right now, but she mailed me a test. Uh, and that's okay too. That's more expense to you. And I didn't usually put that as an option, but guess what? She used it. It worked. It got here. So,
The address is 4504 Claremont Avenue, Birmingham 35222, right?
okay, you did say 4504, didn't you? Okay, yeah, that's correct. Okay.
Okay, I'm gonna mail mine today.
Okay, you can do that too. I didn't want to put it out there because I knew that would be an expensive mailing, but if that's most convenient for you, you certainly can do that. Okay. Um, let me see. Any other questions? I think I hit all the possibilities there. All right. If there's not any, let's get going on today. We're still in Chapter 2, Polynomial and Rational Functions. Today we're starting 2.5, which is zeros of polynomial functions. And in my mind, this is the most important section in Chapter 2 so far, especially in the polynomial part. And this is the last section in the polynomial part. The next section will be rational functions. We do everything with rational functions in one section. Okay, so that's pretty important too. But at least for the polynomials, this is the culmination of everything we've done so far. Okay, so this is an important one. I'm so glad I'm able to record it. I'm so glad I'm able to write on the screen. So let's go for it. Okay, any questions so far? All right, the objectives here, a bunch of them. It's an important section. We'll use the fundamental theorem of algebra, that sounds pretty important, doesn't it, to determine the number of zeros of a polynomial function. Now, we've already sort of used that a little bit when we talked about the maximum number of zeros. Now we'll talk about the number of zeros, okay? We'll find rational zeros of polynomial function. Now, that's a whole new procedure, but it's pretty easy procedure. And then we'll talk a little bit about the conjugate pairs of complex zeros, but you see that wasn't in our course description, so I'm going to go through that pretty quickly, okay? And then we'll find the zeros by factoring. That's pretty important, okay? And then we'll use Descartes' rule of signs and the upper and lower bound rules. That's 3 different rules there to find zeros of polynomials. Actually, Descartes' rule of signs has 2 parts to it, so it's almost like there's 4 different pieces there. But those are extra tools. I think of this as that you're putting tools in your tool belt to be able to come up with the zeros. That's what we're looking for. All these are tools that you'll use to try to find those zeros. And then it says you'll find zeros of polynomials in some real-life applications. That's going to be putting those tools to work in a pretty simple problem. An interesting problem too. Okay? Any questions so far? Okay. We're going to start with the fundamental theorem of algebra. Boy, that sounds pretty impressive, doesn't it? Now, again, we're getting into complex number systems. But remember, all real numbers are complex numbers, so we've already been in the system. Now we're including those that have imaginary components to them. So in the complex number system, every nth degree polynomial, that means if it's a second degree polynomial, the n is 2. If it's a 7th degree polynomial, the n is 7. Okay? And it says here, every nth degree polynomial has precisely n zeros, which means a quadratic always has 2 zeros. And you might say, wait a minute, we found some that have only 1 zero, and we found some that have no zeros. Well, those are real zeros. We're talking about complex. Any that are missing in the real number system have to be complex, meaning imaginary components to it. This important result is derived from, it's not exactly what it says, derived from the fundamental theorem of algebra, first proved by German mathematician Carl Friedrich Gauss. He lived way back there, okay? If you think about the years of his life, He was born 1 year after we declared independence. We were still fighting the Revolutionary War then. But of course, he was over in Germany. He didn't know anything about that. It didn't matter to him. He was a baby anyway. But he lived up until 1855, which would have been, 5 years before the war between the states happened. So you reference everything in regard to wars. That's not very good, is it? But anyway, by the way, since we're talking about that, I wanted to commend 1, 2, 3, 4, 5, 6 of you for getting your research papers in. Way to go. But that means way more than half the class hasn't turned those in, and we're in our last month, folks. So please get those in this month, okay? In fact, sooner the better, okay? So Carl Friedrich Gauss may be a potential thing. Fundamental theorem of algebra may be a potential topic. There's lots of topics out there. So here's what the fundamental theorem of algebra says. Now, to me, this doesn't sound very impressive. And here's what it says. If f of x is a polynomial of degree n, we were talking about this before, where n is greater than 0, in other words, you can't have a polynomial of degree n minus 1 or n or 0. It just doesn't happen. Polynomial of degree n greater than 0, 1 or more, then f has at least 1 0 in the complex number system. Well, big whoopee doo, That doesn't sound all that impressive, okay? But that extends, and since he proved that theorem, then they've extended it and found any nth degree polynomial, n greater than 0, has precisely n zeros. Not just 1, but n. But that would include those that are real zeros and those that have imaginary components. We're not going to worry with imaginary components, but we'll just acknowledge that they're there. Okay? So, using that fundamental theorem of algebra and the equivalence of zeros and factors, you can obtain the linear factorization theorem. This is all on page 152. If anyone's just getting the book open, this is chapter 2, polynomial rational functions, 2.5, zeros of polynomial functions. First page in that section, page 152. If f of x is a polynomial of degree n, as long as n is greater than 0, n 1, 2, 3, 4, 5, any of those numbers, then n has precisely n linear factors. Okay? What that means is f of x is equal to, it can have some coefficient. We're going to call that coefficient a sub n. Okay? That's going to be the coefficient up front. And then the linear factors will be x minus c1 times x minus c2 times x minus c3, dot, 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 all the way up to x minus c sub n. So you have n of those linear factors. Okay? But now those c's that you see there are not necessarily real numbers. Many of them may be. In fact, all of them may be. Or most of them may be. But it could be that they're all complex numbers with imaginary components. And remember back when I said that quadratic equation that had no real zeros? Guess what? Both of its factors are complex, meaning, well, they're all complex with imaginary components. So that's why this is still true. Okay? So, remember C's, complex numbers, that can be real numbers. All real numbers are complex numbers, or it can be complex numbers with imaginary components. Okay. Now, that fundamental theorem of algebra and the linear factorization theorem only tell you that the zeros exist. They don't tell you how you find those things. That's what we're going to be doing. Such theorems are called existence theorems, and in many ways are not really all that practical, except to let you know they're out there somewhere. You just have to find them. So that's our task for the rest of this section, finding those zeros, finding those factors. So that's what we're about here. So here's example 1, bottom of page 152. And by the way, this one's also located at larsonprecalculus.com. You can see an interactive version of this type of an example. Okay, so the A part here. The first degree polynomial, f of x is equal to x minus 2. Okay, what they just told you it was first degree. How do you know that is a first degree polynomial? What gives it away? Anyone know? Look at the maximum exponent you have in that polynomial function. What is it in this case? Do you even see an exponent? No. So what do you understand it to be? No, 1. If that was just minus 2, f of x equal minus 2, that would have a 0 exponent because it would be x to the 0, which is 1. This has an x in it, and when you don't see an x, just like you don't see the coefficient. So what do you understand the coefficient to be? If you don't see 1 there, you understand it to be a 1, just like the exponent. So that is a first degree polynomial. That's a linear equation, and it has exactly 1, 0. And that's easy to find. Just set this equal to 0, solve for x, and you get x equal 2. That's just like someone was asking. I sounded like Kaya's voice, but I don't know Kaya's voice. I don't know who it was that was asking. If you had x minus 2 is a factor, which is the only factor here, then that would result in x equal 2. So if going back to synthetic division, so if you're doing synthetic division and this was going into something, you put a 2 on the outside, the opposite of this. But here, because that represents the same thing, you still put a 2 on the outside, but you see you don't change the sign. So when it's written as a factor, you change the sign for synthetic division. When it's written as a value, x equals something, you don't change the sign because it's already been moved. All right, but that's not what we're talking about here. This has exactly 1, 0. So they did the whole problem for you. I don't know why they made this an example. They did all the work, okay? Now, here is what, just pretend you can't see this part. What is the degree of that polynomial? F of x equal x squared minus 6x plus 9. What's the degree? Maximum exponent. What? 2, exactly. Second degree polynomial. Therefore, how many zeros does it have? 2, exactly. It has to have 2. But we're going to see a little problem here. Now this one, what we're doing to find the zeros, you set it equal to 0. That's what a 0 means. The polynomial is equal to 0. Find the x values that make that true, and you found the zeros of the function. So how would you suggest we proceed with that? How would you solve that? What's the F word? Factor it. Let's see if it's factorable. It may not be. If it's not factorable, you use the quadratic equation. And if you remember how the quadratic equation goes, it starts with minus b plus or minus what's inside the square root, right? So you see there's 2 solutions, the plus solution and the minus solution. And then it's over 2a. But yeah, that's okay. That's where you get your 2 solutions there. Let's see if we can factor this. Only possible factorization for x squared is x times x. Perfect. Then we go and pay attention to the sign of the last term. That's a plus. Now what that means is these 2 signs here and here have to be the same. We look at the middle sign and see it's negative. So that means both of these have to be negative. Now we have to come up with a number, 2 numbers, that multiply to be 9 but add to be 6. 3 times 3, perfect. Okay? And here is where the ups comes into play. Because this tells us if these 2 factors multiplied together is equal to 0, that means that either x minus 3 is equal to 0, or x minus 3 is equal to 0. Hey, it sounds like I'm stuttering. I said the same thing twice. Well, this solution would be add 3 to both sides, and that gives us x equals 3. And this one would be add 3 to both sides. I'm repeating myself again, and that gives you x equals 3. Well, in reality, that is only one solution. But because it happens twice, we call it a multiple, a double root, you might say, a double solution, okay? So that does count as two solutions, x equals 3 or x equals 3. Now, let me just, I don't know if this is helpful to you or not, but if we were plotting that, this is a quadratic, so it's going to form a parabola. X equals 3 is your 0, and it goes up like this and up like this. It only touches the x-axis at one point, not two. But if it was anything less than that, like plus 8 would have been there, that might have been down here. Plus 10 would probably have been up here. Plus 8 would have had two solutions. Plus 10 would have had no solutions. They both would have have imaginary components. This one has two solutions. They just happen to be the same number. Okay? It sounds a little silly, but it's true. We call that a repeated 0. And we say that this has x equals 3 is a 0 with a multiplicity, and we'll talk about this later, multiplicity of 2, meaning it was this factor here was x minus 3 squared. Whatever the exponent is, that's the multiplicity of that. So if that would have been x minus 3 cubed, that would have been 3 threes there, you know. That would have been a solution 3 times. Okay. All right. Now, let's see how they did that. They probably didn't go into that much detail, but let's see what they did. They factored it and see that you do have two factors, but they're identical, has two zeros, they're identical, x equals 3, x equals 3. That's called a repeated 0, or a 0 of multiplicity of 2. We're going to get that terminology later, but I thought let's go on and say it now, because you make sure you've heard it before. All right, now here's one. The third degree polynomial function. If you're trying to find the zeros, which is what the whole problem is about, let me see, I did that. Oh, seems like we've had some new people add. Let me see who's here. Somebody must have come in I didn't have before. I had Cormisha, Kaya, Courtney, DeAndre, Drake, Jay, Cameron, Keelan. Kennedy is here. Excellent. I didn't know you came in. Glad. By the way, I got your letter. Kennedy Clayton. There you are. Okay. Let's see. I think there may be somebody else who has come. Kennedy. Already had Latrissa. Minuet. Good deal. Good to see you or hear from you that you're here. Okay. So Minuet's here. All right. Excellent. I think that may be the only two that added recently. Any of the others of you not hear me call your name? I've got Nadiria. I have Olivia. I have Sean. Yeah, I think I've got everybody now. Okay. So let me close that out for now. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good. I'm the 14th. Okay. If you see anyone else pop up, let me know so I can get them on the roll. So here's a third degree polynomial function. What can we do with that? We're trying to find the zeros of that polynomial function. How do we do that? What's your F word? Factor. We set this equal to 0. That's what finding the zeros means. Set it equal to 0. Okay? How does that factor? Normally, I can't factor a third degree polynomial, most of them anyway. But this has a pretty obvious first factor. What would that be? Anyone make a guess? Say again? Did someone say factor out the x? Say yes. All right, I knew you said that. Okay. Factor out an x from both terms. What does that give you for the first term left? X squared plus 4. Perfect. Set that equal to 0. Okay? Now, that gives you a pretty obvious one solution. X equals 0. The other one would be x squared plus 4 equals 0. Okay? What seems wrong with that picture? Yes, x squared plus x squared is always a non-zero number. I mean a non-negative number. It could be 0, it could be positive, but it's never negative. You add 4 to 0, you get 4. You add 4 to any other positive number, you get something greater. You'll never, ever get 0 with that thing in the real number system. So this represents, it's a second degree polynomial function. This represents two roots or zeros with imaginary components. Okay, those are complex numbers. This one's a real 0. This one's are complex numbers with imaginary components. You can't, and for the purpose of the rest of what we do, that's all you have to say. The book is going to tell you what they are, and it's pretty simple. So we'll watch them do it, but we're not going to, get too bent out of shape over it. Okay? So there's your 3 zeros. 1 real and 2 with imaginary components. Okay? That's really all you can say there. Now, another thing you can say here, you factored this completely in the real number system. Okay? You haven't factored it in the complex number system. That's okay. You factored it in the real number system. That's as far as you can factor. And you'll see they come up with the solution. So let's clear this out of the way. Any questions before I clear it? Okay. So let's erase that and see what they do. First thing to do, they factor it. Look at that. Okay? And then they factor the second part, and this is the part you didn't have to do, x minus 2i times x plus 2i. Remember that when you multiply the complex conjugates together, you get a real factor. Okay? X squared plus 4. We just did it in reverse here. So there's its 3 zeros that had maximum exponent of 3. That means you do have 3 complex zeros. There's 1, that's a real one, and these 2 are complex ones. You don't have to worry about the complex ones. That wasn't in our course description, but just know that they're there. Now this is leading to something else. And I'm going to hit it now because it's here in front of us. You just may not realize it. Anytime you have real coefficients here for all, and this doesn't mean integral coefficients, that's what we have. It means any real coefficient. That could be pi, square root of 3, anything as a coefficient. You're going to have, if you have complex answers, they're always going to show up as complex conjugates of each other. Okay? The factors will be complex conjugates, and that means the answers will be complex. These are complex conjugates. That's 0 plus 2i and 0 minus 2i. Those are your solutions. It's just we don't usually write 0. It's plus 2i and minus 2i. They are complex conjugates of each other. Okay? So sure enough, the linear factorization theorem worked. There's the 3 linear factors. That gives us exactly 3 zeros, and that was the degree of the polynomial. Okay. Now, we're going to back up a little bit. Right now, recently, all we've been talking about are real numbers and then complex numbers with imaginary components. Let's step back one more set of numbers. Rather than real numbers, let's go back to rational numbers. Now, what we're excluding here are square roots. We're excluding pi's and e's and all those irrational numbers, and cube roots and fourth roots and all those radical roots, okay? Not all of them, but a lot of them. We're just talking about rational zeros now. Can anyone remind me what it means to be a rational number? Can you give me an example of a rational number? What's the first 5 letters of rational? Ratio. What is a ratio? A ratio is a comparison of two numbers in the division sense. A over B. So in other words, some sort of fractional form. Another way to express that, well, is just a ratio, okay? Now, what can those numbers be? A can be any number any integer in the world, any integer. The B, however, can be any integer except 0, because you can never divide by 0. So a rational number is any ratio of two integers as long as the bottom integer is not 0. Okay? Now, so that's what we mean by a rational zero. So we're going to deal with numbers that look like that. So let's move on. The rational zero test relates the possible rational zeros, these are possible rational zeros, of a polynomial having integral coefficients. Now remember I said that just a few minutes ago that if you have real coefficients and you wind up with an imaginary root or a root that has an imaginary component, they always come up in conjugate pairs. That was for real coefficients. Now we're backing off one more step and making integer coefficients. And most of our coefficients have been integers so far. So that's just nothing too new for us. So if you have, you're looking for the possible rational zeros of a polynomial having integral coefficients to the leading coefficient and the constant term of the polynomial. So basically for the rational zeros test, you're only looking at that first coefficient, a sub n, and the last number. All those in the middle, who cares? Okay, they matter, but not for what we're going to be doing. Okay? Now, I want you to remember what had to be true. This a sub n can be anything, any integer now. All these a's have to be integers now for this to work. Okay? Rational zeros test. They're all integers, but this one cannot be 0. Because you see, if an was 0, that means this is not an nth degree polynomial. Because this whole term would be 0. That would be an n minus first degree polynomial. So we require that a sub n not be 0. So what we're going to look for, using those two numbers, just those two, the constant and the leading coefficient, then every rational zero will be in the form, if it's a rational number, it's going to be p over q, just like I said, a over b, p over q, where p and q... Say again? Is James here? Is that what you said? Okay, let me... Oh, we picked up a couple people. Let me see who we got. Okay. Zach came in. Good deal. Is Zach audible yet? There he is. Okay. Who else? Did someone say James? Who's that? Say that aloud. Jonathan. Jonathan. Got it. Okay. Okay. Got John here. Okay. Is that who someone was telling me earlier? Oh, Kwame. I didn't see Kwame come in. Okay. You see, once I get to teaching and I've got all these things open, I can't see people coming into class anymore, and that's why I'm glad y'all told me. So let me see if I got everybody now. Yeah, I already had Kermisha and Courtney and Drake and Jay and John now. Kaya, Cameron, Keelan, Kennedy, all K's there. What is that? 4 in a row. No, 5 in a row. Kwame, Latrissa, Minuet. Now, they put them in alphabetical order, don't they? Of the first name, or whatever your call is. Olivia, Sean, Zach. Okay. I think I got everybody. There's a total of 17. I'm counting as one of them, so it should be 16 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got it. Thanks for alerting me to that. Okay? Get this out of the way, and we'll go back again. And I don't know, it's all right. Okay. All right, so all your rational zeros will be of this form. Of course, this is a rational number. It's going to be P over Q, where Q can't be 0, of course. But also, P and Q can't have any common factors. So if your leading coefficient, I'm giving things away. If the leading coefficient was, give me a number, any number. Make up a number. An integer. Somebody give me a number. Huh? 2. And the constant term, make up a number. Anybody? 4. Okay, excellent choice. See, 2 and 4 have common factor of 2. So you would only use 2 and 1 then, okay? Because the P and Q can't have any common factors other than 1, of course. 1's a factor of everything. But what is P? That numerator is any factor of your constant term. What is the Q? That's any factor of the leading coefficient. And that's why if that was 4 and 2 or 2 and 4, then you would not have any, you would eliminate the common factors, okay, and just go with what's left. All right. Now that's pretty interesting, maybe at first, but remember these are integers, so you have to deal with plus and minuses too. So let's see. Let's put that, okay. I found out that if I do something with Zoom, then I go back to try to advance my slide, it won't advance. So there we go. To use the rational zero test, you should first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. Now, that sounds complicated. It's really pretty easy to do. So your possible rational zeros are all the possible factors of your constant term divided by all the possible factors of your leading coefficients. Okay? Now, having formed that list of the possible rational zeros, then you have to use trial and error, oh boy, to determine which, if any, are actual zeros of the polynomial. Now, we know a technique that makes that easier. You already know it, and that's why we did it in the last section, or the section before. No, the section before that. Note that when the leading coefficient is 1, that means your denominator is all 1, 1 plus or minus 1. So that means all your rational zeros are integers, because that would be your factors of the constant term. The possible rational zeros are simple factors of the constant term, which of course then would be integers. Okay, so here is our first go. Find all the rational zeros of this function. Well, first, can we do that? Well, yes. All your coefficients, 1, minus 1, 1, minus 3, and minus 6, they're all integers. If one of those had been a minus 3 halves, or a plus square root of 2 x squared, yeah, you can't do that. You can't use rational zero theorem. As long as those are all integers, you can. But you don't care about the others. You only care about that minus 6, well, actually the 6 and the 1. So your rational zeros will all be of the form P over Q, where P will be all the possible factors of 6. Now you can say minus 6, I don't care. You're going to do all your plus or minuses. So what are all the possible factors of 6? Plus or minus 1. That's a factor of everything. You give me the next one. Plus or minus 2. Give me the next one. Plus or minus 3. Give me the next one. Plus or minus 6. You got them all. Okay? And we're going to divide that by all the possible factors of 1. That's easy. Plus or minus 1. Okay? So you've listed all the factors. That plus or minus 1 in the denominator makes it so easy. All your possible rational zeros are just those numerators. That's equal plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. That's all of them. Okay? Now, here's where we start the trial and error. And the first trial is the easiest one to do. That's why I like to do it. Let's try x equal plus 1. Okay? That's what we're guessing. The rational zero, x equal 1. Now, what makes that easy, when you raise 1 to the 4th power, it's still 1. To the 3rd power, it's still 1. To the 2nd power, it's still 1. To the 1st power, it's still 1. So guess what you do? You just add your coefficients, which is 1 minus 1 plus 1 minus 3 minus 6. That couldn't be much easier than that, could it? So let's add all the positives together. Whoops, all you got is 2. Add your negatives together, and that gives you minus 10. Guess what? 1 is not a factor, not a rational zero, because that didn't give you a 0. So plus 1's out of there. Now, do we have to do that with minus 1? Well, we could if we wanted to. But if you remember the factor test that we did with synthetic division, let's do minus 1 into those coefficients. And I wrote them up there, and that's all you have to do, because you put the coefficients of your term. You remember synthetic division? That was a lot of fun, right? 1 minus 1, you continue. 1, negative 3, negative 6. Now, always with synthetic division, I count and see how many numbers I have. 1, 2, 3, 4, 5. Well, that better mean my polynomial must be degree 4. It is. Always one less than the number you have, the number of numbers you have there. So we got it right. There's no missing terms. Remember, synthetic division, you have to put in zeros if you're missing a power. Like if this would have been an x to the 5th, that would have been a 1, and no x to the 4th, you'd have a 0. Okay, but this is fine. Then we skip a line, draw a line. The book says that, I say it. And then bring down the 1. And you go from there. Negative 1. No, negative 2. You're adding. Yeah. And then positive 2. No, 3. You're adding. 1 and 2 is 3. Okay, yeah, oh, you're jumping ahead of me. And then you have you said a negative 3, and then you have a negative 6, then you have a positive 6, and then you have a ding, 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 a 0. That means you found a rational zero, x equal negative 1. So there. Plus 1 was out, but minus 1 is in. Okay? Now, here's a little warning. Remember, you can have multiple zeros. Okay? So therefore, we need to use minus 1 again, just to make sure you don't have a multiple zero, a repeated 0. So let's do it again and see what you get. You see, you don't have to go back to the original. You can do it of the quotient now because you had a 0 remainder. So skip a line, draw a line, bring down the 1. Go to town for me. Negative 1. Negative 3. Positive 3. 6. Okay, you got it right, but there's no 0 there. So -1 is only a single multiplicity of 1, 0. There's only 1 there. So I've got to, that was a good try, but it didn't work. Okay, but you needed to try. Okay, so what do you want to try next? We did +1 just by plugging in because that was so easy. Then we did -1 by synthetic division and found out it was a 0. What you want to do next? Say again? What were your possibilities? Plus or -1, or you've dealt with that? How about +2? Go to town with that one. What you get? 2. What you get here? 0. What you get here? 0. I heard you said. I hope you said. Then you get 3. Then you get 6. And then you get 0. Ding, ding, ding. We have another winner. Okay. Now, so x equal 2 is a 0 of that polynomial function. When you get 3 numbers down here as your quotient, stop synthetic division. And here's why. What do those 3 numbers represent? See, this was an x to the 4th, this was an x to the 3rd, this represents the coefficient of x squared. So this represents x squared plus 3, because there's no x term here, 0x. Set that equals 0. What does that tell you? Tells you you can't do that. Okay, not in the real number system. X squared plus 3 is never equal to 0 in the real number system. What that means is the other 2 zeros for this polynomial are complex zeros with imaginary components. In fact, they're plus or minus the square root of 3i, or I times the square root of 3. So that means there are no more rational zeros. What it said, found the rational zeros, we found 2. The other 2 are complex numbers, not rational zeros, not rational numbers. So therefore, you found what they asked for. X equal -1, x equal 2. You know there's 4 zeros by the linear factorization theorem, so that means the other 2 zeros here are complex zeros with imaginary components. They're not rational. Okay? Any questions on that? This is sort of fun, isn't it? It's like a detective show. You're trying to find the missing zeros here, and there you found them. All right, for me to erase. Anyone still writing? I hope you're writing. Okay. All right to erase. All right, let's see how they do it. Because the leading coefficient is 1, the possible rational zeros are the factor of the constant term, which is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Yeah, we got there too. They just skipped a step, but I wanted to show you the full way of doing it. Okay? And then they applied synthetic division successively. They skipped all the hard part. They didn't show that plus 1 didn't work. They just went straight to -1 because they knew the answer already. Once you got that answer, they didn't show you. You have to try x minus 1 again, x equal -1 again, and when you did, it wouldn't work. So then they went to 2, and sure enough, it worked because you have the 0 remainder. See, that's why I like to pull that off, so you make sure you know that's a remainder. Okay? Now, you stop there because the factors are x. Okay, remember when you write them as factors, you go back and change the sign here. Just like your question earlier, when you're doing synthetic division of a factor, you change the sign. When you're writing it as a factor, you change the sign. That becomes the x plus 1, this becomes the x minus 2, and then this is your last factor, x squared plus 3. This one cannot be factored any further, so you have also factored completely in the real number system that polynomial. You've also found the 2 zeros here and here, the 2 real zeros, rational zeros, and you also discovered the other two zeros are complex numbers with imaginary components. Wow. See how much this told you? You're only looking for the two rational zeros. You also got the complete factorization in the real number system, and you saw that there were two complex roots with imaginary components, all for the price of one. Okay? Any questions? Okay. Because the factor x squared plus 3 produces no real zeros, there's no way you can do anything with that and come up with a real zero, that you can conclude then that x equal minus 1 and x equal plus 2 are the only real zeros. Certainly they're the only rational zeros, but now you know they're the only real zeros, which is verified by this graph here, which we didn't do. But if you had done it, you would find it has a 0 here and a 0 here, but because it's a fourth degree polynomial, that means the other two zeros have to be complex with imaginary components. Now, understand this too. Let's go back. What if this factor would have been an x squared minus 3? Okay? That can't be factored in the real number, in the rational number system, but it can be factored in the real number system. Oh, I think we added somebody else. Let's see, who else came in the class? I just hit that by mistake. Or did we have 15 there before? I forget. Maybe it was. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, I guess somebody left. Okay. We had 17 before, so we must have lost somebody. Okay. Sorry about that. I knew that wasn't the number I saw before. I couldn't remember which way. Okay. What I was saying here, that if you had x squared minus 3, which I can't see now because this other thing's on top of it, that would factor as, say again? Here we go. X plus the square root of 3 times x minus the square root of 3. Those are real factors. Those are real solutions. In other words, x equal negative root 3 and x equal positive root 3. Those are real solutions, but they're not rational solutions. Those are irrational numbers. Okay? So it's not that when you do your synthetic division and get down to that last thing, it's just that you can't factor it. You can't factor it in the real number system, which would include you to be able to have radicals there. But x squared plus 3, no way you can factor that in the real number system at all. This one can be factored, this one cannot be factored. So that gives you complex answers. Okay, just wanted to point that out to you. The graph of this one would have then had another root at, if this had been the answer, root 3 is something a little bit less than 2 and a little bit less here. So it would have been somewhere in there. You'd have had to go squiggle up and down a few times. That's not our problem here. But I just wanted to tell you, just because you can't factor it with integers, if you can factor it with irrational numbers, you still have two more real roots. They're just not rational roots. And that's all we were looking for, rational. Okay. That probably was confusing the issue, but I wanted to say it just to keep you from thinking, we didn't say that. Well, no, I didn't. Okay. So when the leading coefficient of the polynomial is not 1, the list of possible rational zeros can increase dramatically, because now you have all the factors in the denominator, which means some of your rational possibilities, possible rational solutions, could be fractions, and that's fine. Those are rational numbers, but that makes it a lot harder to do synthetic division, but we'll manage to muddle our way through it. In such cases, the search can be shortened in several ways. First, you can use a programmable calculator. That doesn't sound very fair, does it? to speed up the calculations, yes. A graph drawn either by hand or with a graphing utility, that doesn't sound like it's fair, but yeah, you can do that too. Can give a good estimate of the location of those zeros. And the intermediate value theorem, along with the table generated by your graphing utility, can give approximations of zeros. Well, that just gives you approximations. Usually we can figure it out a lot better than that. Or synthetic division, and that's what we just used, can be used to test the possible rational zeros. That to me is the easy way to go. You don't have to have special calculators. You can do it. So finding that first zero is often the most difficult part. Okay. After that, the search is simplified by working with lower degree polynomials, as shown before, attaining synthetic division, as we just did in example 3. But recall that if x equal a is a 0, then x, I don't know what they're going to say here, then x equal a is also a solution of that polynomial equation, f of x equals 0. So yes, and that also means that x minus a is a factor. I thought that's what they were going to say. X minus a would then be a factor of that polynomial, f of x. Okay? So, keep those things in mind. All right. Now, what we just did, I forgot. Oh, y'all let me do that, didn't you? We went straight to example 3. We missed example 2. Usually, they do the first one, but skip the second one. You let me skip example 2. Let's do example 2 real quickly. I don't do anything quickly. F of x is equal to x cubed plus x plus 1. Okay? Now, we want to, all they say here, find, if possible, the rational zeros of that. So what's the possible rational zeros of that? Rational zeros, being rational, are going to be of the form p over q, where p is all the possible factors of your constant term, plus or minus 1, divided by all the possible factors of the leading coefficient, which are also plus or minus 1. So there are the only two possibilities, plus 1 and minus 1. I actually wrote them out that way. Okay? Now we can plug in a plus 1 and see what you get. You get 1 plus 1 plus 1. Guess what? That's not 0. Right? Well, actually, you could also plug in a minus 1, or you could use synthetic division. I don't care which. Synthetic division is pretty easy. Let's try it. Minus 1 on the outside, and then you put your coefficients down. What would they be? You tell me. Coefficients of that polynomial. Coefficient here is 1. No, coefficients. 1. Oops. Notice you're missing the squared term, right? So you have to put a 0 in for the squared term. Then a 1 and a 1. Remember that? You have to account for every term. And how you check? Count how many numbers you have. 1, 2, 3, 4. Has to be one more than your maximum coefficient. Yep, you got it. Okay? Skip a line, draw a line, bring down the 1. What do you get next? Minus 1 times 1. Synthetic division. Negative 1. Negative 1. Positive 1. 2. Negative 2. Negative 1. There are no rational zeros for this polynomial function. Positive 1 didn't work. Negative 1 didn't work. Now, if you look in the book, you see it does cross the x-axis. But guess what? That's not a rational number. It's an irrational number where it crosses. But it only crosses once. What does that tell you? The other two zeros, because this has three real roots, no, three complex roots, the other three have to have imaginary components in them. So one of them is an irrational number, not a rational number, and the other two have to be, and they always come up in pairs as long as its coefficients are real numbers, and they are. They're all integers. But there are no rational zeros, and there's one irrational zero and two complex zeros with imaginary components. We're not going to look for those. We're not going to find them, okay? But it just wanted you to see it isn't always rosy in Mudville, okay? Sometimes things are pretty bad. Now, I forgot to mention, yeah, something at the top of the page 153, I just happened to notice it when we turn back to it. There's another character listed here, and he is the French mathematician Jean-Laurent D'Alembert, or something like that. I'm sure the French would be screaming at my pronunciation. He worked independently of Carl Friedrich Gauss in trying to prove the fundamental theorem of algebra. And so many people in France consider that D'Alembert's theorem, not the fundamental theorem of algebra. So there's another potential paper topic there, okay? Who was D'Alembert and the other mess that goes on there. All right, and we had already done example 3. And by the way, I forget to say this every time. After every example, guess what there is in the book? A checkpoint. And the checkpoints are similar to what we just did, but try to do them after we finish class, sometime when you have time. If you can't get them, go to larsonprecalculus.com and you'll see a worked out solution, audio video solution of those checkpoints if you can't figure them out. So let's move on.
Dr. Paul, I got a question.
Yes.
Do we get bonus points for the survey?
Okay, yeah, okay. I'm so glad you mentioned that. I meant to say at the very first of class. They have opened the student course evaluations. Please do the student course evaluations, okay? Please do them. They are very valuable to us and to everyone at the college, especially in this environment that we're in now. And knock us as much as you want to knock us in it, because I know it's not been easy for y'all either. But to answer your question, no, I count this as a math course, not an evaluation course. So I don't give extra points. I just really encourage you to do that because it is such an important thing. I'm dropping tests, and things like this, so you're going to get plenty of bonus. Don't sweat that part. Just do the course evaluation. Sorry about that. I know some other instructors give points wherever they can find a place to give points, but I figure I'm such an easy grader and such an easy teacher and such an easy everything, it would be unfair for me to just give points anywhere willy-nilly. So, no, I usually don't do that. So, sorry about that. But please do the evaluations. And thank you for bringing it up, because I meant to say that as my first announcement, and I didn't do any announcements. Thank you for saying it. Sorry, the answer isn't probably what you wanted, but thanks for bringing it up. All right. Now, we were getting ready to do example 4, and that's when I realized we hadn't done example 2. So let's see. Yeah, they're skipping 4 and 5, so let's us do 4 and 5. So let's go back where we were. I think it was here. And let's do example 4 and 5. We'll do one at a time, though. Okay. Yes. You're kidding me. Oh, we're just beginning to have fun. Oh, we're always having fun. All right, we will pick up next time with example 4. Okay. And let me give you some homework exercises. I know you're disappointed we had to stop, but at least I won't disappoint you by not giving homework exercises. Okay, so the homework exercises, this is one long section, isn't it? Any of the odds, 9 through 13, they're all at Calc Chat. 9's at Calc View. either 15 or 17, they're both at Calc Chat. Any of the odds 19 to 27, they're all at Calc Chat. 25 is at Calc View. 29 or 31, they're both at Calc Chat. 29 is at Calc View. Either 33 or 35, they're both at Calc Chat. Oh, wait. Let me not go too far here. Yeah, we're okay. 33 or 35, they're both at Calc Chat. Well, let's see. Let me stop. Okay. Those next two examples. Okay. I think everything I've said so far. Oh, we have it done. You might want to stop at 27, okay? Because we didn't solve the polynomial equation. So stop at 27. There's plenty there to work on, plus your research papers, plus any of the tests that you still have out, and your evaluation. So you got plenty of things to work on this weekend. If you don't, try to email me and I'll find something else, okay? Okay, I'll be looking for those emails. Okay. Good deal. We will see you. Have a good weekend. Have a safe weekend. Keep safe. I hope everybody's family's all right. And we'll see you on Tuesday. Is that okay? All right. Be in touch. Bye-bye. All right. Let me end the meeting.
Hey, Dr. Fowler.
Yes.
This woman.
Yes.
I turned in my essay. I had turned the works side page on it.
Okay. Say that one more time.
My essay that I sent you.
Yes.
I sent the other one, and this time it has the works side page.
You did not send the works cited page. Is that what you said?
No, I did send it.
Okay, you did, but what?
Nothing. I'll just tell you that I sent it. Because the first one I sent to you, it didn't have the works side page.
Oh, and you sent it twice. Is that what you're saying?
Yes, sir.
Okay,
Yes, sir.
yeah. I believe I noted that. Let me just check and see. Tommy Owen. There you are. And when did you send the second one?
I'm not sure when I sent it, but I have to look.
But you what?
I have to look at Blackboard.
Okay, I'll try to look too. You sent it through Blackboard?
Yes, sir.
Okay. The one I have was dated the 13th of February, and I think you, yeah, I don't remember when, but it seemed like I got the next one in March. And the thing is, you lost one bonus point, but then you got 1 point for having it. So it basically came out the same score, is what I remember. Now, I may be wrong on that. If you found out you sent me the second one in February, then I'll add another point. Okay?
Yes, sir.
All right. Good deal. All right. Thanks for bringing that to my attention. I probably just looked at it and said, no, I already got his. Okay. So I'll go back and see if I can find it.
Yes, sir.
Okay. Thanks much.
Thank you.
Any other issues? All right. I'm going to end the meeting then. We'll see you on Tuesday.